The last time we discussed about conformal maps. The last two lectures, recall what are conformal maps? Conformal maps are simply one-to-one onto holomorphic maps between two domains in the complex plane. You can define conformal maps on the Riemann sphere to itself also. First of all, you define a holomorphic map from the Riemann sphere to itself by simply declaring it as a meromorphic function on C, such that f of 1 by z is also meromorphic. Okay. Anyway, so we looked at a few examples of conformal maps. In particular, we looked at these Mobius transformations, yeah, along with some other examples. So one of the reasons to care about conformal maps is that they help with solving the Laplace equation, in the sense that if Laplacian of some phi is 0, and if you compose it with a conformal map, it will continue to solve the Laplace equation in the new coordinates. In other words, you can solve the Laplace equation on a complicated domain, provided there is a conformal map from that domain to a simple one like the unit disk. And on the unit disk, solving the Laplace equation is not rocket science, really. There is a formula to do it called Poisson's formula. Yeah. So then we gave a few examples. I didn't prove this. This was a part of the homework. For instance, the weirdest example was this one, and it took the punctured unit disk to C minus -1, 1. Yeah, this was the weirdest one, but we looked at several examples. We saw that in order to sketch the image of these maps, it is instructive to look at the image of a coordinate grid, as in you can look at what happens when x is constant and y is constant, or you can look at polar coordinates when theta is constant or when r is constant, and see what happens to these things. Okay. We define Nubious maps. Nubious maps are simply these kinds of maps where A, B, C, D are complex numbers such that AD minus BC is not 0. Now, Mobius maps are indeed one-to-one. They are conformal maps. In fact, they take the Riemann sphere to itself. We studied their group structure. In other words, you can compose Mobius maps and get a Mobius map. Mobius maps are invertible. Composition is associative. You have the identity map, so they form a group. Yeah. Moreover, I said this: every Mobius map can be written using translations, rotations, scaling, and inversions. Yeah. We looked at the fixed points of Mobius maps. So if the Mobius map is z goes to z, then there are infinitely many fixed points. In all other cases, you have exactly one or two fixed points. You have one fixed point in the case where z goes to z plus a and its conjugates. In all other cases, you have two fixed points. Yeah. We saw that you needed exactly 3 complex parameters to uniquely specify a Mobius map, not 4, as you might naively think, because at least one of these parameters is non-zero, and you can divide it by that parameter and make it 1. Yeah. And we also saw that as a consequence, not really a consequence, but related to this fact, was the fact that given any 3 distinct, it's crucial that they're distinct, of course, points on the Riemann sphere, you can map them to any 3 other distinct points on the Riemann sphere by means of a unique Mobius map. Yeah. And finally, we defined this concept of a cross ratio for 4 points. I could be writing this wrong. Hopefully this formula that I'm writing is correct. It's this quantity. It's a complex number associated to these 4 points. And the speciality of this cross ratio is that if you use a Mobius map, let's call that Mobius map F, then these 4 points go to 4 other points. Yeah? And you can write a cross ratio for those 4 points. That cross ratio and this one will be one and the same. In other words, Mobius maps do not change the cross ratio of 4 points. In other words, the cross ratio of 4 points is an invariant under Mobius maps. Right? Okay, so this is what we did the last time. Before we go on further, any questions? All right, so then let's move on. Okay, so Mobius maps one more geometric property. So the question is, so the cross ratio of 4 points is a complex number, right? In general, it's a complex number. It's not a real number. But the question is, when is this cross ratio of 4 points? One of those points can be taken to be infinity because that makes our job much simpler, right? Because the formula for the cross ratio if Z4 is infinity is a very simple formula, namely this, right? So the claim is it is real if and only if Z1 minus Z3 is alpha times Z2 minus Z3, where alpha is a real number, obviously, right? That is, so what does this mean geometrically? It means the following, that if you take Z3 and Z1 minus Z3, this is a vector taking Z1 to joining Z1 and Z3. Z2 minus Z3, let's say this is let's say this is Z2. This is Z2 minus Z3. This is a real number. What this means in the sense of vectors is this vector is proportional to this. That means that they are both parallel. They are along the same direction. Yeah. So the vector joining Z1 and Z3 is parallel to that joining Z2 and Z3. In other words, Z1, Z2, and Z3 are collinear. So the cross ratio of these 4 points is real if and only if these 3 points, Z1, Z2, and Z3, lie on a straight line. Okay, so that's a very pleasant property, right? So you can directly know when 3 points are collinear by simply computing the cross ratio of these 4 points. Yeah. What about in general? What if instead of infinity I have 4 points? Then it's very complicated, right? The formula for the cross ratio is not as simple as this. Now what can we do? Since the cross ratio is invariant under Mobius maps, what does that mean again? If you take a Mobius transformation, then suppose I give you 4 distinct points, right? If you take a Mobius transformation, you get 4 other points. The point is the cross ratios of these 4 points and these 4 points, they're both equal. So the cross ratio of these 4 equals these 4, provided so since this cross ratio is invariant, we can, so first of all, we know that, let's put it this way, you can, sorry, this statement is not quite correct. So you can make sure that Z4 goes to infinity, Z1 goes to 0, and Z2 goes to 1. This can be accomplished by means of a single Mobius transformation. Okay. And that Mobius transformation is unique. Unfortunately, such a Mobius transformation need not take Z3 to I. So this is actually a wrong statement. I'll correct it later on. So this is not entirely correct. I'm sorry about it. But let us, for the sake of argument, assume that you can map these 4 points to these 4 points by means of a Mobius transformation, for the sake of argument. The cross ratios of these two are the same. Therefore, that means that that means these three better lie on a line. Okay. So what do Mobius maps do to lines? So the point of this statement, which is wrong, this is not true in general. Just because you give me 4 points does not mean I can map them to four other points by Mobius map. The best one can do is to map 3 points to 3 other points. Okay? But let's assume you can map these 4 to these 4. In that case, the cross ratio is invariant. And because we are assuming the cross ratio is real, that means the cross ratio of these things is real. That means these 3 lie on a line. Okay? So that means what happens to this line when you go back here? So a Mobius transformation supposedly takes these 4 points to these 4 points, right? These 3 lie on a line. So what happens to a line under a Mobius map? So this is the real question. Okay. So this is just motivation for this question. Right? Don't take it too seriously. Since every Mobius map is a composition of translations, rotations, scaling, and inversions, we just need to see what each of these operations individually do to lines. So what does this mean? What I'm trying to motivate for you is the following question. If you take a straight line and apply a Mobius map, what happens to it? Why is this a well-motivated question? Why should I care about this question? Well, firstly, this one, right? What happens to cross ratios? If a cross ratio is real, what can you say about these 4 points? That's the question that motivated this. All right. So what do these things do to lines? What do Mobius maps do to lines? Now, every Mobius map is a composition of these very simple ones. So in order to find out what a general Mobius map does to a line, you just need to know what these things do to lines. Okay. All right. So translations, rotations, and scaling take lines to lines. Of course, right? If you have a line, you translate by a complex number, you go to a line. If you have a line and you scale it, it'll just be another line, which is just a larger or smaller version of it. If you have a line and you rotate it, it'll become another line. So if you take translations or rotations and scaling, they take lines to lines. So in other words, if I apply these one after the other, this line goes to some line. Okay. What about inversions? What happens when you apply this map to a straight line? That's the question. Okay. So what is a straight line? Y equals mx plus c. That represents almost all straight lines except for one straight line, namely x equals a constant. Right? This is not included in this formula, but I'll leave this special case as an exercise for you. Okay. So take the straight line. So y is z minus z bar divided by 2i, and x is z plus z bar over 2. So when you substitute x and y here, you get the complex equation of a straight line, namely this. Yeah. So as I said, actually, this is not the most general equation of a straight line. Actually, the general equation of a straight line is ax plus by plus c equals 0, because this does not take into account x equals c. But anyway, it's not very hard to see that, I'm sorry, let me just erase this. It's not at all hard to see that the most general complex equation of a straight line is this. This is a special case of this because basically what I'm saying is take all the z's and the z bars to one side. So you get z to 1 minus im minus z bar times 1 plus im. So this is 2IC, right? In other words, if I call this complex number A, AZ minus A bar Z bar is I times, 2IC, right? So I times a real number K times the imaginary part of A. Why? Because, sorry, I should not have had imaginary part of A. I should have had the real part of A, because the real part of A is the number 1. I could have thought of this as 2 times I times C times 1. Again, I'm sorry for this typo. It should have been the real part of A. Doesn't matter much, as you'll see. So this is a straight line, yeah. So when W is 1 over Z, then if I replace W as 1 by Z, I get A by W minus A bar over W bar is something, I times something, should be the real part technically. Therefore, you can see that A W bar minus A bar W is mod W square times something. We don't care what it is exactly. So that means that now you can complete the square. You can say that, let me put a real part here. You can complete the square, right? Because I can divide by this quantity on both sides. I can say that AW bar minus A bar W divided by K I real part of A is mod W square. And I can complete the square and I can get this, right? So let me just remove this. Once again, there's a typo. It's not the imaginary part, it's the real part. Now, what sort of a geometric object does this equation represent?
Circle.
Yeah, that's a circle, right? It's centered at minus of this point with this radius, yeah? Which is a circle, right? So now we need to see what happens to circles under these maps. So the problem is, we started off with the question of what happens to lines under Mobius maps. If you apply translations, rotations, and scaling, they go to lines. Unfortunately, if you apply an inversion, a line can potentially become a circle. Now, if you apply Mobius maps, what happens to the circle, right? You need to know what happens to circles under these maps. All right. A general circle centered at Z0 with radius R is mod of Z minus Z0 square equals R square. Circles clearly go to circles. Why? If you take a circle and you translate it, of course it's a circle, right? Only its origin changes, this equation and this equation. If you rotate a circle, what does that mean? What that means is, if I take this circle and if I rotate it, it will just become a circle somewhere else. If I scale it and rotate it, what will happen is it will probably go further and get rotated, right? Nonetheless, it will still remain a circle. Okay. The real question is, what happens when W equals 1 by Z? So when W equals 1 by Z, what happens? 1 by W minus Z0 square equals R square, which means you get this, right? So when you expand this out, by the way, the best way to expand these things out is this way. right? Remember, a bar is mod a square. So this is 1 plus mod z naught square mod w square minus z naught w minus z naught bar w bar. So when you do that and you bring the w mod w square to the other side, when the dust clears, you get this. Yeah. So what is this equation? What does it represent? How does one figure out what geometric object this equation corresponds to? So how does one do that?
If mod z equals r, then it represents a line.
Okay.
Otherwise, it will represent a circle.
Right. And how do you figure it out?
So write W as x plus iy.
Sure, absolutely. So one way to do it is to write w as x plus iy, and if you have you will get a quadratic and x and y, and there is a standard way to know whether a quadratic represents a circle, an ellipse, a hyperbola, a parabola, or a pair of straight lines. Right? This is like 11th standard or 12th standard geometry. But so let's see that there's a more elegant way. So if mod z naught square equals r square, then this term goes away. Then you'll see that this is the case. And by what we just discussed, this is precisely the equation of a straight line, right? If not, we again have a circle, and the easiest way of seeing these things is you write this, you divide this beast by mod z naught square minus r square plus this. You write it as 0, and you complete the square. In the sense, suppose you have mod z square minus aw minus a bar w bar plus blah equals 0. Blah doesn't involve mod, w. Then you can say that w minus a square, w minus a bar square, e plus whatever is there is mod a bar square. Why? Because this is mod w square plus mod a bar square minus aw minus a bar w bar, which is precisely this, right? So completing the square, you don't have to always go back to Cartesian coordinates. That's the point I was trying to make. Anyway, the point here is that we again have a circle. In other words, generalized circles, namely straight lines and circles, go to generalized circles. Okay. In what sense? Why am I calling a straight line a generalized circle? In what sense is a straight line a circle?
So radius is infinity.
Exactly, right? The radius is infinity, basically. So generalized circles, namely straight lines and circles, go to generalized circles, namely straight lines and circles under Mobius maps. Okay. Why? Because every Mobius map can be written in terms of translations, rotations, scaling, and inversions. Each of these maps takes these generalized circles to generalized circles. Lines either go to lines or circles, and circles go to either lines or circles. Okay. Right. Therefore, the cross ratio is real if and only if the points lie on a generalized circle. Okay. Why is this statement true? Let's go back here. This is, of course, this statement is incorrect. Okay. Let's call this something, say W. Okay. So the cross ratio does not change under Mobius maps. We can always take this to 0, this to 1, and this to infinity by means of a Mobius map. No problem. This will go to some W. We don't have any control over what it goes to, but we don't care. Yeah. Now the bottom line is the cross ratio of these 4 points is real if and only if the cross ratio of these 4 points is real. Why? Because the cross ratio does not change when you use a Mobius transformation. And the cross ratio of these 4 points is real precisely when these three lie on a straight line. Okay? So if these three lie on a straight line, yeah, that means that, so if these three lie on a straight line, what happens to that line under, so there's a Mobius map that goes from here to here, under the inverse, that straight line goes to either a straight line or a circle. That means Z1, Z2, Z3 lie on a straight line or a circle. Okay? And the same is true with any permutation, right? If you take Z2, Z3, Z4, you could have applied the same argument. You could more or less, you could have applied the same argument and so on and so forth. I leave it to you to think about it, but I claim that this much is enough to guarantee that points lie on a straight line or a circle. Okay? In fact, 0, 1, W and infinity, all of them lie on one single straight line, right? So, and that straight line goes to a straight line or a circle. In other words, these 4 points lie on a straight line or a circle. It's much simpler than what I was just saying. But yeah, okay. The only thing that needs to be corrected is that this is not true. This has to be some W. We don't have any control over it, but that doesn't matter. All we know is this is real if and only if all 4 points lie on a straight line. That means all these 4 points lie on a generalized circle. Okay. All right. Okay. Any questions so far? All right. So there are no questions. Let me move on. So now I'll do some examples of Mobius maps. What do I mean by doing examples? Of course, if you take AZ plus B over CZ plus D, if you plug in your favorite values for A, B, C, and D such that AD minus BC is non-zero, that's an example, right? That's not what I mean. Okay, what do I mean? Let's see. The key point here is how do you determine the image of a Mobius map, right? Write down an arbitrary Mobius map. How do you know what its image is, right? I give you the domain and ask you to determine its image. How does one do that? Now, one can't always do it in a very nice way, but if your domain is a very nice kind of a domain, then you can do it. Okay? What do I mean by these seemingly vague statements? Let's do some examples and try to find out. So to determine the image of a Mobius map, it is enough to look at 3 distinct points. Okay. So what does that mean? In what sense? Suppose I take these 3 points. Okay. Let's say they all lie on a circle. They do not obviously lie on a line. So if I want to determine what a Mobius map looks like, if I determine where these 3 points go, that is, suppose for the sake of argument, I know that these 3 points go to 3 other points that lie on some other circle. There is a unique map that goes from here to here. So on paper, I can determine where every other point goes. Okay. But this is too vague. We'll just have to see what this means more concretely. Moreover, Mobius maps take the interior of a circle to either the interior or the exterior. What is the meaning of this phrase? What is the meaning of the interior of a circle going to the interior or the exterior? First of all, what is the meaning of the interior of a circle? Let's take your favorite circle, say mod z equals 1. What is the meaning of the interior?
Mod z less than 1.
Yeah. And the exterior is this. Okay, so this is the interior and this is the exterior. I claim that suppose I take a Mobius map from C to C, then if you take the interior, if you take any circle, suppose this circle goes to another circle, not to a straight line. Suppose the circle goes to a circle. Okay. In fact, maybe, yeah, suppose the circle goes to a circle. I claim that the interior of this either goes inside this or outside this. Right? So how does one prove that? That requires a little bit of work. The easiest way to prove it, actually, maybe I'll just leave it as an exercise. Why don't you think about it? How do you prove this statement? That if I have a circle, a Mobius map takes the interior, suppose the circle goes to another circle under the Mobius map, then the interior either goes inside this circle or outside. In other words, completely, I mean, this goes completely here. That is, this is a one-to-one onto map here or a one-to-one onto map to the outside. Now, this is obvious for special examples, right? If I take z goes to 1 by z, what happens to the unit disk centered at the origin? This interior goes here, the exterior goes to the interior, right? Suppose I take a translation of this thing, z goes to z plus a, this goes to another circle centered at a, the interior, of course, goes to the interior. If I take a rotation, the interior goes to the interior, right? And the exterior goes to the exterior. My claim is, in general, Mobius maps, I mean, this is true for any circle. I claim that z goes to 1 by z takes a circle centered somewhere else, its interior to its exterior, and so on. Okay. If you choose a circle that goes to a circle. Now I understand I'm being a little vague, but yeah, maybe it's best if you try to see this sort of thing on your own. Anyway, these facts allow us to construct various examples. In what sense? So first question, find a conformal map that maps the upper half plane, that maps this, where y is positive, to the interior of the unit disk. So you want to map this to this. Well, how? How does one try to solve such a problem? So the idea here is whenever you want to construct a Mobius map with specified properties, the idea is all such Mobius maps must take the boundary to the boundary. Okay? In other words, I want a map, a Mobius map that takes this straight line to this circle. How can I ensure that this straight line goes to this circle?
By exponenting, sir.
Sorry?
if we take exponential function,
That is not a conformal. I mean, what do you mean by the? You're saying you want to take z goes to e raised to z?
no, I just
Or
want this line portion to go to the boundary, right?
I understand. No. What I want is a map from C to C that takes this line to this circle. I want it to be defined on all of C.
Okay.
Sir,
So, yeah, you're right. In principle, you can try this. I'm not denying that. But the problem is this has other problems. It won't be one-to-one on all of this. I want this to be a conformal map here. That means I want it to be one-to-one on the upper half plane. So this won't work. Sorry?
Sir, we can suppose that such a map is Az plus b over Cz plus d. Then we can simplify it by using the properties of the upper half plane.
Right. So first of all, okay, let us first agree that the map we are looking at is actually a maybe. Sorry, am I interrupting someone? Okay, fine. So yeah, first of all, let us agree that the conformal map that we are looking for is a Mobius transformation. So instead of saying this, maybe I should have, to make it easier for you, I could have said, find a Mobius map that does the job. So you need to find these numbers so that AD minus BC is non-zero. That takes the upper half plane to the unit disk. And I claim that these properties tell you that if you manage to take the boundary to the boundary, then this part either goes inside the unit disk or outside. Okay. So at the very least, we'll be in very good shape if you manage to take this straight line to this circle under this Mobius map. So the question is, how can I choose A, B, C, and D so that this straight line goes to this circle? Is the question clear?
Hello, sir.
Yeah.
Sir, we can take 3 points, 3 distinct points on the straight line and map to 3 distinct points on the circle, sir. And there will be unique Mobius map, sir.
Very good, very good. So in other words, if you take 3 points, your favorite 3 points on the straight line and map them to your favorite 3 points on the circle, then surely, since Mobius maps take straight generalized circles to generalized circles, they will take this straight line to either a straight line or a circle. However, these 3 points go to 3 points that are not collinear. That means that this straight line must go to this particular circle. That is forced on you. Now that this thing goes to this, all you need to check is whether this goes inside or this goes outside. That is the only thing one needs to check. Okay. How will you ensure that this, so let us say, how will you ensure that this goes inside as opposed to outside?
we just need to take one point in the upper half plane and see where the image lies, either inside or outside.
Excellent. But there is a small problem, no? 3 points uniquely determine a Mobius map already. So if you choose 3 points and make them go to 3 other points, you've already fixed the Mobius map. So as someone just pointed out, you can verify whether this goes inside or outside by taking a point here and seeing where it goes. Does it go inside or does it go outside? But the problem is, what if it goes outside? You're in trouble, right? Then what will you do?
Then perhaps we choose some other 3 different points.
That is one way to do it. There's another way to do it. How else will you correct this problem? Suppose I manage to come up with
invert it.
Then you compose it with z goes to 1 by z. Okay. So I hope this strategy is clear. I'll implement it in a moment. Don't worry. But I hope the rough idea is clear. Okay. So since the boundaries are generalized circles, we can try our luck with a Mobius map. We need to take two boundary points, namely my favorite points on a straight line are 0 and 1. Two boundary points, 1 and I. This is 1, this is I. So the boundary can either go to a circle containing 1 and I, or to the line passing through them. That means this thing, if you just do this much, then this can either go to this line or to a circle, to one of the infinitely many circles passing through these points. So we need one more thing. So what we'll do is we'll take minus 1, 0, and 1 to go to the left of 1, because this, you see, is on the left side of this. So if you want to preserve the orientation, you should take this to minus I. Then you have some hope of this going inside. That's the idea. Okay. Right. So let's check whether this works. Surely the boundary goes to the boundary. However, we must be careful in that the upper half space should not go to the exterior of the unit circle. If it does, if you found the wrong map, simply invert it, simply compose it with z goes to 1 by z. Nonetheless, let us check what kind of a map we end up getting. Let us check what happens. Since f of 0 is 1, az plus b over cz plus d, what did we demand? That minus 1 went to minus I, 0 went to 1, and 1 went to I. So f of 0 is 1, so that means b over d is 1, so b equals d. And AD minus BC should not be 0. So in other words, AB should not be BC, that means B should not be 0. So we can divide by B and pretend that it is actually 1. Okay. So f of z is, maybe I should have written it as a tilde and c tilde. They are two different constants, but that's okay. We can abuse notation and write them as a and c. Now f of 1 is I, therefore a plus 1 by c plus 1 is I. That means a plus 1 is I times c plus 1. Likewise, f of minus 1 is minus I. So minus a plus 1 divided by minus c plus 1 is minus I. So you can just solve these two simultaneous equations. If, for instance, if you subtract out, you'll see that 2a equals 2i. So a is I, and likewise c is minus I. Yeah. So in other words, the bottom line is f of z equals iz plus 1 divided by 1 minus iz. I claim this does the job. Let us just verify. Let's see. F of 0 is 1. Great. F of 1 is I plus 1 over 1 minus I, and this is indeed I. And f of minus 1 is minus I plus 1 over 1 plus I. Yeah, this is also I, minus I. Okay. But we also need to check what happens to something here. Suppose you take the point I here. What is f of I? It's minus I square plus 1 over 1 minus I square, which is 0, which is inside the unit circle. So if one point goes inside, everything else also goes inside. Okay? So thankfully, this is the correct map. Okay? So we have successfully managed to conformally map the upper half space to the unit disk. Okay? So if we know how to solve the Laplace equation here, we know how to solve the Laplace equation here. Is this clear?
Sir?
Yeah.
Sir, we have taken the point minus 1 to the left of 0. And then on circle, it is minus I point. So how we determine left on the circle? left or right on the circle.
What I mean is, if I go from here to here, suppose I have a particle traveling and it's at t equals 0, it's here, t equals 1, it's here, and t equals 2, it's here. On the circle, it should travel in the same direction, right? It should go from here to here and then here to here, as opposed to from here to here and here to here. Is it clockwise or anti-clockwise? That's the difference. But don't worry too much about this, okay? Just find 3 points, send them to 3 other points, get a map, just check if that's the correct one or not. If it is not the correct one, no problem. Just use z goes to 1 by z at the end of the day to get the correct one. Okay, not a problem. Don't worry.
And sir, this map is not unique also, because if you take some other 3 points on circle, then we get another map.
Absolutely, that's a very important point. What you're trying to say is, in fact, if I have a map from the unit disk to itself, there are lots of conformal maps that take the unit disk to itself. That is the automorphisms of the unit disk. There are lots of them. Okay, so yeah, it's not unique by any means. By no means is it unique, right? Right? Yeah.
Yeah, okay, sir.
Any other questions?
Sir, can you talk about Laplace equation here? What you are saying about that?
Laplace equation of this type, Laplacian of phi is 0, p equals a given function g on the boundary of this unit disk. This can be solved by means of a formula. That formula, if you want to Wikipedia it, it's called Poisson's formula or Poisson kernel or whatever it's called. Okay, this can be done easily. Now, if I ask you the same question on the upper half plane, h on this line. If I ask you to solve this problem, what you can do is you can solve this problem and use that Mobius map. That is this function, say phi tilde, is simply phi composed with a Mobius map. In other words, you have a map from here to here, f, right? So just take phi composed with f. That will be the solution here. And that is what I'm trying to say.
Okay, sir.
Okay. Right. I'm lying a little bit because when I say this and this, I mean, yeah, that has to be. What I'm saying here is, if you want to solve this, maybe I'll be a little more concrete. Let me be a tad bit more concrete. What I mean is, suppose the problem is solve this, and over here phi is g. What does that mean? Phi of x comma 0 is some g of x. Okay. So I claim that if you take this thing and solve some Laplacian, say not phi, let's call it psi equals 0. Psi equals g composed with f on the boundary. If you solve g composed with, g is from here, g composed with f inverse. Okay. Now, whatever solution you get, if you take psi composed with f, that is the solution you want. You can basically transport the problem here to the problem here and come back. There's a dictionary that goes between these two, and that is this Mobius map. Okay. Sorry, I mean, maybe I was a little vague, but I hope I'm clear. All right. So let's go to another. Yeah.
Sir.
Yeah.
Sir, Mobius transformation maps interior of a circle to either interior or exterior of a circle. But in upper half plane, how we determine interior and exterior?
What I mean is, it takes one side of the circle or the line to one side of the circle or the line. That's what I mean.
Okay, so is there any precise definition for interior or exterior of a circle or any reason?
Yeah, sure. I mean, in general, the precise definition is if you take, okay, let's only restrict to circles and straight lines. If you take a line, it divides the plane into two connected components. If you take a circle, it also divides it into two connected components. I claim that a Mobius map that takes this line to the circle will take one connected component to this connected component to one of these components, this connected component to one of the other components. That is the precise statement.
There is one statement that bilinear transformation takes circles onto line, circles onto circles, and circles onto lines. That means the circle can go to circle or circle can go to line. Line can go to circle and line can go to line.
That's right, but what I'm saying is a little more.
Yeah. Yours is more general statement.
Right.
Yeah, yes.
Right.
Sir, so that
yeah, sure. Sorry. Yeah.
so that in this example, if we wanted to take the exterior, we will simply take the inverse.
Yeah. So whatever you get finally, this one, if I take 1 by f of z, then it will take the upper half plane to the exterior.
Yes.
Yeah, absolutely. Any other questions? All right, let's look at another example. Hopefully this will also be a little illuminating. Sorry, what? When should I stop? What's it? From 5 to 6:30. Okay.
6:30.
Okay. Fine. Yeah, good. So the other question, the other example is map the hemidisk, namely this one, conformally onto, that means 1-to-1 holomorphically onto the upper half plane. Oops, let me. Yeah. Okay, so this is the question, right? Now this is a little tricky, okay? Because naively, if you try to use a Mobius map, okay, this straight line will probably go to the straight line, but what about the circle? It will go to something else, right? But that's a problem, right? You see, the point is, this beast here, it seems to have two things as its boundary, a part of a circle and a part of a straight line. On the other hand, there's only one thing that seems to be the boundary of this, right? So there is a trick here. It is not obvious as to how to do it. There is a small trick. I hope people appreciate the difficulty of this problem. Any comments?
Sir,
So
please.
can we take x greater than one part to x greater as in negative and positive?
I beg your pardon?
So like we are saying that straight line will go to the straight line, but we want the curve to also go to the boundary, the straight line of the other part.
So ideally, you're right. You would ideally want to take this to, say, this part and this to this part, something like that, right?
Right. Yes, sir.
Yeah, but unfortunately, a Mobius map cannot do that. Because how will you ensure this? You will say that, okay, take 2 points here. They'll go to other points here. Okay. But that does not fix the Mobius map, right? If you want this straight line to go to here, you'll have to take one more point here and one more point here, but that already fixes it and you have no more freedom here, right?
Right.
So
Yes.
There's something tricky here, and there is a neat trick. Okay, the trick is as follows.
Sir, can we take z square first?
Well, z square, all it will do is this. It will take this to focus, right? Doesn't help. But you're on the right track, but you should not be taking z square first. The trick is as follows. These are the crucial thing. This is where some change happens, right? Look at these two of the circle with the real axis to 0 and infinity using a Mobius map. That sounds like an odd thing to do. I'm saying take this point to 0, take this point to infinity. When I do this, what happens to this line and what happens to this semicircle? What do you think? So a line must always go to a line or a circle under a Mobius map. By the way, please do not make the mistake of assuming that straight lines and circles go to straight lines and circles under any conformal map. That is false. Only Mobius maps have this very special property that they take generalized circles to generalized circles, okay? Not anything else, okay? Let me make this abundantly clear. But anyway, coming back to this, we know that a Mobius map takes this straight line to a straight line or circle. We know it takes this to a straight line or circle. But precisely what kind of a geometric object does it take each of these if I do this? Does this go to a straight line or a circle? Let's start with that. Yeah.
So if we have a map like that, the upper arc will go arcwise and this straight line will go lower arc.
No, I'm merely asking you whether this goes to a straight line or a circle, that's all. A part of a straight line or circle, fine. But whatever it is, does it go to a straight line, a part of a straight line, a part of a circle?
Part of a circle, I think.
Are you sure? You see, bear in mind, I'm taking one point on this line to 0, another to infinity. No circle can contain infinity.
So we wanted to go it to upper half plane, so technically it should go to a line.
No, we wanted to go there, but this is not in one step. This is not going to solve the problem we want. So that's why I'm asking a much simpler question. All I'm saying is I'm taking this point to 0, this point to infinity. So from that, what can you deduce? Does this go to a straight line or a circle? And the answer is it
should go to a straight line.
Straight line, because a circle can never contain infinity. Circle is a bounded object, right? It's a compact thing. It never contains infinity. Likewise, this circle also cannot go to a circle because two of its points are 0 and infinity. That means it must go to a straight line. Meaning these two go to two straight lines like this. So this entire base, this semi-disk, goes to a sector. Is this argument clear? I hope this argument is clear. So this hemi-disk goes to a sector. Now, we have one more degree of freedom, right? We only use 2 points. Mobius map needs one more. The semicircle goes to a ray from 0 to infinity, and likewise for the real segment. We get a sector which, so I need to, so I have not been complete here. So all I'm saying is under any Mobius map that takes this to 0 and this to infinity, this thing goes to a sector. What I'd like is for this to go to this precise sector. Where, sorry. So what I'd like is for this to go to, I mean, this line. So I'd want this line to be a part of the real axis. Okay, so I want this to go to some point here so that this goes to some sector like this. Okay, something like this. So I can just make sure that this point goes to some point here so that it goes to a sector like this with some angle. All right. So let me just tell you again. Using an appropriate Mobius map, I can make this go to this. How can I make this go to this? And here comes another trick that one of you was trying to suggest. Just take z goes to z raised to n. So we get a sector which can then be rotated using z raised to n. Indeed, the Mobius map is 1 plus z over 1 minus z. Why is it 1 plus z over 1 minus z? What does this Mobius map do? This point is minus 1, this point is plus 1. So minus 1 goes to 0, plus 1 goes to infinity, 0 goes to 1. Let's see where some point inside goes. I goes to 1 plus I over 1 minus I, which is what? 1 plus I over 1 minus I, so if you multiply by 1 plus I and divide by 1 plus I, this is 1 plus I square plus 2I divided by 1 plus 1, which is, this is 0, so this is just I. In other words, this point goes to a point, sorry, I is here, I'm sorry about that. This point goes to this. Okay, so in other words, this goes to this particular sector. Namely, the sector consisting of the y-axis and the x-axis, the first quadrant. So when z is, in fact, you can prove this more rigorously, when z is real and when z is larger than minus 1, that means if you look at this particular straight line, the image is real and positive. So that means this particular straight line goes to the x-axis. When mod z is 1, then z is e raised to I theta, where theta is between 0 and pi. Therefore, the image is 1 plus e raised to I theta, which is 1 plus cos theta plus I sine theta, by 1 minus cos theta minus I sine theta. This you can simplify. 1 plus cos theta is 2 cos squared theta by 2, plus sine theta is 2 sine theta by 2 cos theta by 2, by 2 sine square theta by 2, and this is minus 2i sine theta by 2 cos theta by 2. Okay, so the 2's get cancelled out, so you'll get cot theta by 2 times, I think, cos theta by 2 plus I sine theta by 2 by sine theta by 2 minus I cos theta by 2, something like that. This is just I. Anyway, just a very quick calculation tells you that this image is purely imaginary. In other words, this goes to this and this, but this goes to this. Okay. It's a right-angled sector. So z goes to z square takes this right-angled sector into the upper half plane, because it rotates this down here, it preserves this, so it goes to this. So in other words, the final map that we are looking at is this 1 plus z over 1 minus z squared. I know this is a little tricky. It requires some thought. Is the basic idea clear?
So, sir, here square term is, so it is not a Mobius transformation.
It is not. It is a composition of z square and a Mobius transformation. I'm not saying that you can solve all the problems in conformal maps using Mobius transformations. You might have to be a little clever and use a collection of things. Mobius transformations are just one weapon in your arsenal. You have others too. That's the thing.
So like this, in this we got a right angle sector. What if we wanted to be at some angle sector, not the right one?
What if we wanted, sorry?
We here we got a right angle sector. Instead of right angle, if we wanted some other angle, maybe some acute angle sector.
So if you want, you don't have control over what kind of a sector you would get. We got lucky here and we got a right angle sector. But if your question is, suppose we did not get a right angle sector, suppose we got a sector of angle, 45 degrees, then what will you do? Well, then you take z goes to z raised to 4. Well, just hope for the best and take z goes to z raised to some power, and so that power rotates this sector like this. Okay, you have to choose some appropriate power. What power depends on the situation at hand. Okay.
So if we get some fraction power, then
yeah, sure, you can do that also. You can raise complex numbers.
In that case, analyticity we need to check, right?
No, but it depends on the branch you choose. You see, I mean, fractional powers are perfectly okay as long as you consider the right branch and so on. And anyway, we don't care what exactly happens on the boundary. We only need to map this here. Okay, so that's okay. We don't need it to be analytic on the boundary. We just need it to extend continuously to the boundary. So not a problem.
So, sir, we cannot construct the Mobius map which maps this this to some acute angle sector that way, as in we don't have a control over that.
In the sense that not a Mobius map, but once you get a right angle thing, suppose you want to make it acute angle, just take the square root.
Oh yes, right.
Right, for instance.
Yes. Yeah. Okay, yes, I got it. Thank you.
Yeah, you're welcome. Any other questions? All right. So
can you repeat what's he saying again?
No, her question was, suppose you wanted to map this semicircle to this sector with, say, angle 45 degrees. What we managed to successfully do is to map this to this sector, right? She wanted to map it to this sector. I said, you can't do it with a Mobius map, but you do this and take the square root. Then you'll get this. That's what.
Sir, can you do like this? First we upper half plane, so we make it upper semi-disc. So we make it complete disc by squaring it.
You won't get a complete disc. That's the problem. You see, when I said hemi-disc, I mean the open one. So when you do squaring, what you will get is not the full disc, but you will miss out the real axis. That's the problem.
Okay, sir.
Yeah.
Yes.
Any other questions? All right, let's move on then. Okay, so maybe you're sick of Mobius maps, but we'll do more of them. Yeah? So as automorphisms of the Riemann sphere, what the hell does that mean? So theorem, and this is genuinely a theorem because it requires some work to prove. The automorphisms of the Riemann sphere, what the hell do these fancy words mean? Meaning the collection of conformal maps from C to itself, which is, I'm sorry, I'll just, which is meromorphic one-to-one functions f from C to C, so that f of 1 by z is also meromorphic and one-to-one. Okay. So the collection of all such conformal maps are precisely Mobius maps. In other words, Mobius maps are examples of conformal maps of the Riemann sphere to itself. My claim is these are the only conformal maps. There are no other conformal maps of the Riemann sphere to itself. The automorphisms of the Riemann sphere are precisely Mobius maps. Okay. It's easy to prove that these are automorphisms of this, but all automorphisms of this are these? That's not easy, right? That requires some work. How do you know that every automorphism looks like this? That's not at all easy. So this requires a lot of work, and that is why it's a theorem. So proof. Given an automorphism F, by composing it with Mobius maps, we can assume without loss of generality that f of 0 is 0, f of 1 is 1, and f of infinity is infinity. Why is this true? What does this statement mean, and why is it true?
And sir, suppose f maps 0, 1, infinity to some other points, then we take another Mobius transformation which maps those points to 0, 1, infinity.
Excellent. Excellent. And we know that Mobius maps are automorphisms of the Riemann sphere, right? And composing two automorphisms gives you an automorphism.
Yes.
Right? So if f does not do this, you're saying you take f composed with some Mobius map, and this is also an automorphism, right? So if you prove that this is a Mobius map, that means f is itself a Mobius map. Okay? So if you manage to prove that this thing is a Mobius map, then f was originally a Mobius map to begin with. Okay? Right. Now, since it is one-to-one, f is an entire function. I mean, it's not. So, what is the meaning of this phrase? Yeah, what is the meaning of this phrase? First of all, what is the meaning of an entire function? I hope you've seen this terminology.
Yes, f is complex differential everywhere.
Yes, so f is a holomorphic function on the entire complex plane. It has no singularities whatsoever. How does the fact that how does f being one-to-one from the Riemann sphere to itself, and along with these things, ensure that it has no singularities on the complex plane? What does one-to-one have anything to do with these things?
F is meromorphic, so it cannot take pole. It has only pole at infinity, because in other point it cannot take infinity.
Absolutely. Okay. The only places where f can take infinity is infinity itself, because no, it's one-to-one. It cannot be infinity anywhere else. That means f it does not have any poles on C. That means it's a holomorphic function on C. Okay. Now, because it's an automorphism of the Riemann sphere, f of 1 by z is meromorphic, right? And f of, so if I define h of z as 1 by f of 1 by z, what happens? Near 0, it is holomorphic. Why? Because what can go wrong? What can go wrong is that this can become infinity. In other words, this can become 0. But when can this become 0? This will become 0 only when 1 by z is 0. In other words, z is infinity. In other words, this function is holomorphic near 0 and h of 0 is 0. In fact, this function is entire. Okay. Therefore, if h of 0 is 0 and h is a holomorphic function, if you take, say, z, I'm sorry, it's not, it's h of z divided by z, this is a holomorphic function near 0 that does not vanish at 0. Why? H of 0 is 0. It's a holomorphic function. So h of z is divisible by z, right? If you write down its Taylor expansion, it starts with z, a0 times z plus a1z square and so on. So h of z is z times some function g of z. The point is g of 0 is non-zero. Why is it non-zero? Because the derivative of h is at 0 is simply g of 0. And the derivative of a one-to-one function is not 0. I mean, in fact, actually, maybe it's not one-to-one. So I claim, sorry, this is wrong. This is h. H prime 0 is not 0. And how does one prove it? One has to use this formula and the chain rule. I should have given it as a homework problem. Yeah.
Since f is 1, 1, can I not say h is 1, 1 also?
Yes, actually, one can directly say that h is 1, 1. But what I'm talking about is h of, yeah, that is true. You can directly say h is 1, 1 because f is 1, 1, and you're taking 1 by f of 1 by z. Yes. So this is the easiest way of seeing. And 1, 1 functions have their derivatives do not vanish. This we know. Holomorphic 1, 1 function, the derivative does not vanish. So anyway, the bottom line is this guy is a holomorphic function and it's not vanishing. So now if you define g of z as f of z by z, when z is non-zero and g of 0 as f prime 0, the bottom line is g is an entire function, g of 1 is 1, and g is never infinite. G of infinity is also bounded. Okay. So why is this statement correct? I urge you to think about it. I mean, only when you think about this will you understand. So this is not correct. Okay, this is maybe right. So the bottom line is whatever this is going to be an entire function that is bounded. And do we know anything about entire functions that are bounded? I hope this has been covered.
Constant.
Yeah, every entire function that is bounded is a constant. That means f of z, g of z has to be equal to z because g of 1 is 1. I mean, not g of z, f of z equals z because g of z is a constant, g of 1 is 1, That means that constant is 1, so f of z equals z. Which means that that means any automorphism that takes these 3 points to these 3 points will have to be the identity map. That means every automorphism is a Mobius transformation. So this is a tricky proof. I'm not saying it's easy. You need to certainly think about it a bit. There are some typos that I'll correct later. But yeah. Okay, please think about this. Right. Yeah.
Sir, any Mobius transformation which fixes 3 points is necessarily identity map.
Yes.
So,
but I'm saying f is not necessarily a Mobius transformation. That is what I want to prove. I'm merely saying f is a conformal map from the Riemann sphere to itself. I want to prove that it is a Mobius transformation. So I'm proving that suppose it fixes these 3 points, it is actually identity. Therefore, it is a Mobius transformation. That is what I'm proving.
Oh, yes, okay.
Okay. All right, let me just, we have 5 minutes. So let me maybe end with this slide. So the question is, which Mobius maps take the upper half plane to itself? We know that there are lots of Mobius maps, and there are lots of them that take the upper half plane to itself. You just take 3 favorite points over here, they'll go, and 3 favorite points here, make them go to these things, then, and make sure that this goes to this, then you'll get lots of Mobius maps, right? So the question is, which ones take the upper half plane to itself? Okay, I hope the question is clear. Not everything does that job, right? Because there is one Mobius map that takes this to the unit circle. So clearly this is not the kind of a map that I'm looking at. So when does a Mobius map take the upper half plane to itself? In particular, it ought to take this line to this line. It should take the real axis to the real axis. In other words, AZ plus B over CZ plus D must be real when Z is real. And if I take this point I, that should go somewhere here. That means its imaginary part must be positive. Okay, this is precisely when this is the answer to this question, but I want a more concrete answer. Okay. So when Z is real, that means when Z is Z bar, W is also real if and only if AZ plus B over CZ plus D equals A bar Z bar plus B bar over C bar Z bar plus D bar. So you just cross multiply these two to get this equation. So when you expand this out and when the dust clears, you get Z squared times something plus Z times something plus something else equals 0 for all real values of Z. Notice this is an imaginary number. This is imaginary, purely imaginary. Like this is I times a real number. This is also imaginary. This is also imaginary. Okay, so we have a quadratic equation of this type. Okay, so if you throw out this, you have a quadratic equation where these are all real numbers. And this is true for all real numbers x. That means each of these coefficients must be 0. Note that the coefficients of the quadratic are purely imaginary. We also know that a real quadratic is identically 0 if and only if all its coefficients are so. That means AC bar equals A bar C. That means AC bar is real. AD bar plus BC bar equals A bar D plus BC bar, which means this is real. and BD bar equals B bar D, so that means this is also real. Okay. Moreover, one of these is non-zero because AD should not be BC. If both of them are zero, then you're in trouble, right? So that means without loss of generality, you can divide by A to begin with and assume that it is 1. Okay? So that means C bar is real, so C is real, BD bar is real, and A is 1, so this is real. Okay? So let B be x plus IY and D be U plus IV. And if you substitute these criteria that this is real and this is real, then you see that V better be equal to Y times C. And if you when the dust clears, the bottom line is you will see that all of them are real. Okay? This is a calculation you ought to do. I won't go with this. So the point is, the bottom line here is, maybe I've written this bottom line here. So the Mobius maps that take the upper half plane to itself are of this type, where these are all real numbers and AD minus BC is positive. So A, B, C, D are real and AD minus BC is positive. These are the Mobius transformations that take the upper half plane to itself. Not all Mobius maps do the job, precisely these ones do. In fact, some people, they demand that AD minus BC be equal to 1. Okay? A, B, C, D are real and AD minus BC equals 1. Okay? Yeah, maybe I'll just stop at this point.